Okay, good morning everybody. Let's go through the earlier talks, just the titles of the slides, and then begin today's material. So we are setting up this Chow homology theory, Chow groups, for algebraic schemes over a base field K. And so we began by saying what are algebraic schemes over a base field K, and then I told you in outline what were Chow groups, graded abelian groups. And the cycles for these Chow groups came from closed subvarieties. So we talked of varieties, closed subvarieties, and these were in bijective correspondence with their generic points, and those were all points of X. So another way of parameterizing was with respect to points of X, naturally stratified into different transcendence degrees of the residue field extensions over the base field. And so we were able to define algebraic cycles as finite formal linear combination of primitive elements defined by individual closed subvarieties. Now, at this point began the work of saying that when is one cycle equivalent to another? There are far too many of these cycles. When is one equivalent to another? And for that, our choice of equivalence is called rational equivalence. And at the end of this series of lectures, we will justify that rational equivalence in terms of a universal property which results from taking that equivalence. That equivalence is forced on us by a certain universal property. So to describe this rational equivalence, I had to talk of rational functions on varieties and where they vanish to what order, where they are poled to what order. Okay. So that we did, order of vanishing, and for that we had to do some algebra which was generalized from the algebra of discrete valuation rings. So that we did and set up an order of vanishing in terms of length of certain Artin rings, Artin local rings. So that we could do at the generic point of a codimension 1 subvariety because it was an Artin local ring. Okay. And that allowed us to define the Weil divisor, Weil divisor, Way divisor, which are what here is the right way of saying it, of a rational function on a variety, which kept tab of all its zeros and all its poles with all their multiplicities and made a linear combination where the coefficients was the order of the zero or pole. And that finally gave the definition of Chow groups. Take the group of all cycles and go modulo those which are rationally equivalent to 0, and that is your Chow group. So by the end of the first lecture, we had definition of Chow groups themselves in our hand. By the way they were defined, it was clear that they are functorial with respect to isomorphisms. But we want more functoriality properties. In my lectures, I am only going to focus on functoriality with respect to proper morphisms, 1, and 2 flat morphisms of constant relative dimensions. But as I have been telling you, one needs far more functoriality, and already you can see in the lectures of others that there is now a need for pullback by a closed inclusion of, say, an effective Cartier divisor. This is not flat, very, very far from flat. And it's a pullback. So even though the inclusion is proper, we want to pull back the Chow point. So one needs much more, but this proper push forward and flat pullback are the foundations in terms of which all these more complicated things are defined. So after having defined Chow groups, we quickly went through how they had the expected dimensions. One of them was Chow group of an affine line. Then there was Chow group of affine space. While talking of Chow group of an affine space, I made the statement that, oh, there is some point, close point there, and now take a line through it. And our friend Supravat showed with a nice example of a finite field that you might have a close point in An so that there is no k rational line passing through it. So my answer to that was, okay, take an affine line over the finite extension of fields, which is the residue field of that. That line now is not a closed subvariety of that An. So Prabhat, that line to this AN is only a proper morphism. Why proper? It's a finite extension. So this is a proper morphism, and now we can complete the argument because we have proved proper push forward. On that line, that point is an F rational point and is the vanishing of a polynomial in F. So it's rationally equivalent to 0. That point upstairs has degree 1, right? Its residue field is F. And what was the residue field of the point below? F. That's where F came from. So what is the degree of that point over the point below? 1. So what is the push forward by definition of the cycle defined by that single point? Itself. And that was rationally equivalent to 0 upstairs, and this line over F mapping into affine space over K is proper. You can see it in 2 steps. Line over F mapping into affine space over F, closed subvariety. Affine space over F mapping to affine space over K, that's the base change of spec F over spec K done to affine space. That's proper. Okay. So this is proper, so pushes forward, and therefore it is rationally equivalent to 0 down there, and so A0 of affine n space is also 0. So even to settle this simple example, we had to use the theorem, or at least what I can think of now. Maybe there are other clever proofs which don't need this. Anyway, eventually we are going to prove that all Chow groups of the affine space are 0, but for the nth group, and the nth group is Z, generated by the cycle defined by all of n. Okay, so then we talked about Chow groups of projective line, and there came the notion of degree. And we said that a meromorphic function, a rational function on P1 has as many zeros as it has poles and whatnot. And using this, we showed that a single k rational point, for example, infinity, is what generates the 0th Chow group. And first Chow group generated by Z. So Z, Z. But eventually we'll prove that for any Pn, the Chow groups are Z, 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 Z. Okay. So then we started talking about proper push forward. For that, we first talked of the degree of a proper surjective morphism of varieties. Okay, this proper surjective comes up because you are going to take the fundamental cycle of a variety and going to define it. What's the push forward? You are going to take its image, which is closed, and this restricted map is proper, and you are going to talk of its degree of this surjective map. So this proper surjective came only while telling you where this goes. The overall map x to y is not supposed to be surjective. It's not required to be surjective. It can be if it wants to be. Okay. So our push forward is for all proper morphisms. While defining that push forward, we talk of proper surjective. Yesterday there was some confusion on the part of some students, so I thought I'll take this opportunity to clearly say where surjective comes in. Okay. So we did that, we defined proper push forward of cycles by taking the degree of the extension as the multiplier on that image if they are of the same dimension, and if they are of different dimensions, this is 0. One simple way of taking care of it, not very illuminating, is to define the degree to be 0 in case the extension is not finite. This is unnatural, but I didn't decide to give that answer. So better say it in these many explicit steps that if the dimension actually decreases, define it to be 0. If it does not, define it to be the degree, which happens to be finite when the dimension is the same. Okay, so then our main job was to prove that proper push forward of a Weil divisor is rationally equivalent to 0. We showed that it is really a Weil divisor through norm of that rational function upstairs, which becomes a rational function downstairs. And more general rational equivalence is defined in terms of Weil divisors of individual rational functions on closed subvarieties. It's a linear combination of those. So each one going to something rationally equivalent to 0, so all of it goes. And therefore, the push forward on cycles went down to push forward Chow groups. So to show that this push forward preserves rational equivalence, while divisors go to while divisors, whatever, we had to make cases in terms of dimension. If the dimension was dropping by 2 or more, then physically the cycle was going to 0. If it was not dropping at all, if the relative dimension was 0, there was this algebraic argument based on norm. And when the dimension was dropping by 1, that was the most interesting geometric case, and that we solved by going to the generic point of that variety below and localizing there, and which was codimension 1 in the variety. Okay. So we have codimension 1 subvariety, closed subvariety of a variety below. We localize there. That's and we want to count its coefficients. So we look at this, take its inverse image, codimension 1, so that is the curve, etc., etc. And then we brought in what we had already proved about, well, we hadn't already proved it because the fiber may not be P1, it may be some other complete curve. So that needed us to show that the degree of a divisor on any complete curve is 0. That we did using the relative dimension 0 push forward argument by saying that any complete curve is finite over P1, and on P1 we had it, etc., etc. So that's how we finished proving all 3 dimension cases and got our desired push forward result on Chow loops. And then in the last part of yesterday's talk, we started taking a look ahead at flat pullback, and I told you guys to go revise your basic knowledge of flat morphisms, and you should still be doing that, it takes some time. And I recommended, for example, the excellent textbook of Altman-Kleiman and its flatness chapter. Hartshorne also has something, or any other modern book. I particularly like all books written by Mumford because they have the balance that I like between very interesting examples and any technology that's needed, he can bring it in. Okay? They are not written under the pressure of the American textbook market. No, I mean, after all, book to be commercially viable, whatever. Anyway, so, and it's an Indian edition. The Mumford, so here's a little commercial. There is this book Mumford, Algebraic Geometry 2. It's printed in India, nicely hardbound, and it's published in Delhi by Hindustan Book Agency and kept at a very affordable price. And go buy a copy. There's nothing like having a copy which you can open anytime instead of booting your laptop to read something online and whatnot. And this is a wonderful book, and considering all of you already know some basic algebraic geometry, you can read and appreciate it more easily. It might not be such a good idea to begin your algebraic geometry with this book. Perhaps Red Book might be better there, or if you have already started with Hartshorne, then you are well prepared to shift to this, or in parallel. Okay, so I am not going to spend time on explaining things about flatness. I take it that you will take care of that, and during discussion I will ask some specific questions. So let's begin today's stuff. So today we are going to talk about this stuff. The first thing is the fundamental cycle, as it is called, of a closed subscheme. And I want you to be able to geometrically visualize. Okay, we have nearly run out, but I have enough for today. But for future reference, you might want. Okay, so how does a closed subscheme look? So here's my scheme, that's the affine plane. And I want a closed subscheme. It looks something like this. This is how a closed subscheme looks. Okay? What are its irreducible components? They are closed subvarieties. One of them appears to be this, another appears to be this thin thing inside this. third is this, fourth is this, fifth is this. Seems to have 5 irreducible components. Now, this by itself doesn't look like a variety, it has a certain thickness. This point looks thin, but this has a thickness. Here there seems to be a thick part on this otherwise thin curve, and here seems to be another thick part. So are thick parts here and here on something which looks smooth. So all such stuff you have learned in your theory of associated primes, primary decomposition and whatnot. Okay. So you guys go and revise your knowledge of associated primes. Okay. So to quickly say what is an associated prime. So we are in a situation where my ring is Noetherian and I have some module over it. And then a certain prime P in A, this is not visible to that side, right? P in A, and I have this module. So when is this an associated prime? So when A mod P has some injective homomorphism into M. Am I right, Jugal? Okay. So that's when P is an associated prime. This is a quick way of saying what are associated primes. And the kind of things that I would like you to know is any finite module over an Noetherian ring has finitely many associated primes. Their set is known as the ass of the ring. Okay. And something can go and kill some non-zero element of the module if and only if it's in the union of the ass. The outside things are the non-zero divisors. And this is very important where the module is the ring itself. You may be interested in what are the zero divisors in a Noetherian ring. And then that's the union of ass. What if your ring was a one-dimensional domain? How does a one-dimensional what would be its ass? So if it's a one-dimensional domain, what are the associated primes? Only 0. Okay. So in general for a domain, what are the associated primes? Now suppose I have one-dimensional Noetherian ring, local. I have one-dimensional Noetherian local ring. What may be the associated primes? How does a one-dimensional Noetherian local ring look? I should draw the picture. So if A is a one-dimensional Noetherian local ring, first of all there is a maximal ideal, so there is a point. And then there are certain prime ideals which are components going through it. Each of this is one of the minimal primes. This is the maximal ideal. However, they may have thickness. There may be some amount of thickness here. M might be an associated prime. May or may not be. And then some of these may have some thickness and whatnot. So how do I quantify the thickness along an irreducible component? Think in the affine situation, if I have spec A, an irreducible component of spec A corresponds to what? A minimal prime. Minimal. Okay? Containment gets reversed. Irreducible component means the biggest, which means the prime is the smallest. So the minimal prime is the irreducible component. What is the thickness there? So you see, there may not be much thickness along this component, but here it is meeting the maximal ideal where there might be some thickness. So you want the thickness in general, not at this special point. Generic thickness is what it translates into. So if I take this prime number Pi and this was spec A, I take A localized at Pi because it's a minimal prime. Inside this, see its scroll dimension is 0. I don't have primes inside this. Okay? And so the Pi is the only prime. So this being dimension 0 and it's Noetherian, it's artin local, it has a length. That length is the amount of thickness in general along that component. So in general, if I have a variety in a scheme, I want to know what what are the thicknesses of its various irreducible components in that variety. Or I might have a certain scheme and I might have its irreducible components and I want to know what is the thickness. I can address the question affine in an affine open neighborhood and take this length. So more generally I will write X is a scheme, Y, X irreducible component. That means OXY, which remember in our Fulton inspired notation is the stock of X at the generic point of Y. This is Artin local. And then I simply take its length. This is the multiplicity, sometimes called geometric multiplicity of X along Y. How thick is this component Y of the scheme X? So have you understood this? There's one more comment I like to make because it will become perhaps relevant at some point later. You know, when I told you that over discrete valuation rings there's a simple valuation telling you order of vanishing, and that says it lies in a certain power of the maximum ideal and not in the next. This works for any Noetherian one-dimensional local ring, and so I can extend the definition of order of vanishing to such ones. Okay. Let's take it a domain so that when I go modulo something non-zero, it is Artin. But then, in the nice examples of Noetherian local domains over K with residue field K, this was also the dimension of that Artin local ring as a vector space over my base field K, right? So you might ask, why not just define the length as dimension of that Artin local ring over the base field K? The answer is we also want to deal with such Artin local rings, and they are not finite over K. This Y may be higher dimensional, may not be a point. And even if when it is a point, its residue field may be something different. Now you may say, okay, residue field is something different. So the dimension has gone very high up, infinite dimensional in case it was higher dimensional. Now at this point, one may say, I don't know whether you will immediately think of this idea, that why not put the residue field inside so that you are back to the, well, the residue field can be put inside through formal smoothness or the, what are fields Q and FP called? What? Basic fields? Prime fields, okay. So the prime field, you know, is always perfect. And what is that residue field is therefore a separable extension of the prime field. And this is an Artin local ring. So by the formal criterion for smoothness, you can always put in the residue field inside. Then it's called coefficient field. So this argument I just now said formal criterion of smoothness, right? This is a kind of stuff which unfortunately is not there in the standard basic textbooks. So Altman and Kleiman is an excellent source for smoothness, etalness, whatnot, but will not have this kind of stuff, formal, blah, blah, blah. Perhaps some modern books do have it. Otherwise, the Niagara Falls is always there. Go with your glass. I want a drink of water. Okay. So, anyhow, right. I think, no, the younger members of our team will be able to guide you better on modern textbooks, I hope, or your own friends, because what I have learned from are very old sources. Okay, so coming back to this. But a word of caution, you can put that residue field inside, but you cannot guarantee that it will contain your base field, and so several other things can go wrong. Okay? So all this you can look up in any bibliography of any book you have, commutative algebra book, under the name of Cohen structure theorem, and see what complications can arise. Okay, I won't say anything more about it. All right. So I have described to you how a scheme, algebraic scheme looks. An algebraic scheme has various irreducible components, and those irreducible components have various generic thicknesses. Those thicknesses are given in terms of the lengths of the corresponding Artin local rings at those generic points, and those are Artin local rings because these were components. So their localizations became of dimension 0. Besides this general thickness along components, there can be some special amount of thickness along various subvarieties. And that algebraically is the phenomenon of embedded primes. Isolated primes, embedded primes. Yeah, you must have heard such terms in perhaps even Atiyah MacDonald says such things which was 100% ununderstandable to me when I read Atiyah MacDonald, and was 100% formally understandable as shown by my score in the exam. But really nothing went in. It's very easy to formally do those manipulations, remember them and put them out in the exam, but really you understand what all that means after drawing pictures, or at least for me. I must also admit, it was surprising to me, but I must also admit, there are people called algebraists. No joke. They have an understanding of that algebra. They have intuition in it. They can foresee what to do. They can do those tricks. And they are not carrying the baggage of geometric pictures. So different human beings have different talents, different ways of approaching something, and for a geometer it's all visualization. For me, pictures is everything. Use algebra, use analysis, use topology, but the thing is pictures. But for them, there is a special algebraic intuition. So if you have that, you are fortunate, and leverage it to be a good algebraist and also learn geometry to help you do algebra. Okay, so so I have told you what is the fundamental cycle of an equidimensional scheme. Equidimensional means all these irreducible components are of the same dimension. So I have scheme and I have, which is pure dimension n, so I don't have these sutter-futter points and other components, smaller dimension thing, they are all out, okay? Because I am only interested in the top dimensional ones. So a scheme which has all irreducible components of the same dimension is called equidimensional. And I take those components, take their multiplicity, and then multiply by that multiplicity and add them up. That's called the fundamental cycle of that equidimensional scheme. I can define this fundamental cycle for any scheme in any way. I might say, oh, take all irreducible components and take their sum. It won't be a homogeneous thing in the graded group. Or I may say, ignore all lower ones and only keep that, whichever. But I am only going to talk about it for equidimensional schemes. So I explained to you what is the fundamental cycle. So the fundamental cycle of W is the element. Take all components of W, which are Wi, and make this formal linear combination of Wi's, where the component Wi is weighted by its thickness, which is this multiplicity. Okay? Alright. So if W is a closed subvariety, okay, then there is only one component itself. And what is the multiplicity of that component? 1. What is going to be the local ring there? The RW. It's a field. Okay. So field has length 1 over itself. It's a one-dimensional vector space over itself. And so, so this definition, though W is also a closed subscheme, and so there is this definition of W. On the other hand, to any closed subvariety we associated this class W, and they are the same. So there is no ambiguity. When I define fundamental cycle of a closed subscheme, if the closed subscheme were a closed subvariety, I would get back what I already defined square bracket W to be. So here's an exercise, and now you can rapidly answer in your mind what it is. So I take the affine plane and I take the closed subscheme to be defined by this, and I'm asking what is the fundamental cycle of this. Okay, so what do you think it is? 3 terms, right? One of them with what multiplicity? Okay, alright, good. So let's go. So now I am going to define this flat pullback, and I won't go on saying flat of constant relative dimension. I'll just make a short form flat. Okay, but it's really flat of constant relative dimension. So when I have something of flat of constant relative dimension, if I take some closed subvariety of Y and take its schematic inverse image, that is of dimension d extra. It is n plus d dimensional because flat of constant relative dimension. So it's a pure dimensional subscheme, but it may not be a subvariety. Something connected, its inverse image need not be connected. Take affine line to itself defined by x goes to x square, and then take a point apart from the point at 0, take some other k rational point. Something, if you are working over certain field like real numbers, choose something which has a square root in that field. Then there will be two different points there. It's a subscheme and not a subvariety. Or if I had chosen my point to be 0, the inverse image will be what? Under x goes to x square. What's the inverse image of 0? No, scheme. Yeah. Kx by x square. So this fantastic scheme kx by x square, known as dual numbers, tangent vector in weighting, that will be the inverse image. It's not reduced. It's Artin local. Its length is 2. So when I pull back this closed subscheme, I get a closed subvariety. It's pure dimensional, but it's not reduced, and its different irreducible components have multiplicities. Like in this example, it was 2. There may be several components, and each may have some multiplicity. Therefore, I will take its fundamental cycle, and that I will define to be the pullback of the basis element of the cycle group below generated by that closed subvariety. So this is the definition. Inverse image of this cycle is the fundamental cycle of this closed subscheme, and it lies in Zn plus d because all the components of this are of dimension n plus d, because V was n dimensional and this was of relative dimension d. And so I got this cycle there. And now such square bracket V's is what generates the free abelian group Z and Y. So I have told you what to do with each generator. So by the universal property of free abelian groups, my volume dropped because I am ashamed to say this again and again and again. You know it so well. But so therefore I get this map. Okay. So now I am interested in functoriality. So I am not just going to pull back once. I am going to do pullback by a composite, and I am going to compare with composite of a pullback. So first time I pull back, the variety turns into a scheme, and second time I am pulling back the scheme. So I should know what happens to the fundamental cycle of a scheme under pullback, because the variety pulls back to the fundamental cycle of scheme. And pullback of a scheme is pullback of the scheme. Okay? Or in algebraic terms, I have an A module M and an A algebra B, then I take B tensor M and make it a B module. But then I have B algebra C, and I take C tensored over B with B tensored over A with M. And that is naturally isomorphic to C tensored over A with M, where C is an A algebra via the composite. Yeah? So this is what is the algebra behind saying that pullback of a scheme is what? Pullback by the composite. So if this taking fundamental cycle commutes with taking pullback, then that will guarantee that pullback of cycles is functorial. And I also know that by the identity morphism of a scheme, pullback of any closed subscheme is itself. So all functorial properties will be satisfied. So I simply have to show that pullback of the fundamental cycle of a scheme is the fundamental cycle of the pullback scheme. That's a simple exercise. Lemma, this is the lemma. Oh, I want to go through rapidly through the proof next. See, you guys are a capable audience. So when I prepared these slides, I didn't exactly know what to expect. So I wrote certain things, and to many of you these are obvious, but let's nevertheless rapidly go through it. Okay? So this is the algebraic lemma involved. Actually, something more is true. This is the something more that is true. So in my notes, I have written something more. Let's quickly look at the proof of this. You see, since we are pulling back things and we are talking about length, we need to know how pullback is related to length. And this also tells us where flatness comes in. Okay? So let me ask you, if I have field extension and I have vector space over the base field, and I take tensor product with the top field, what is the dimension of that over here? Product of the degree and the original dimension. So the degree of the field extension comes up. When I base change my vector space from my lower field to top field and I want to know the length of that, the degree comes up. Yeah? So that is exactly this formula. Alright. So, what's happening here is, where does degree come up? So, because the only simple module, so now let's go to rings. Over rings, this won't be true without flatness. Because after all, I might have the same residue field. And I might have just, I might have an Artin local ring below and just the close point above, then the residue field is the same. And I take the Artin local ring below and it has a certain length. And I pull it back upstairs, I only get that field. And the length has suddenly become 1 there. And below it was something higher. Because the multiplier is just... But what happens in flatness is, I take a filtration of M to get its length, its Jordan-Holder filtration. And each graded piece, because I am an Artin or local ring, each graded piece is what? Residue field, A mod M. Now when I pull back, this filtration remains a filtration because injectivity of each step going to next is preserved by this tensor product because that is flat over this. And so the length now, the same number of pieces as below, except that each piece now has a certain length over below, which is the degree of the extension. This is why this formula. Okay. So we apply this to our Artin local ring below and pull up, and that will give you that blah blah blah. You can read what is written there. So I explained why this formula works. Where flatness comes in, most important. Okay. So with this now we have functoriality of pullback, because that formula showed that the pullback of the fundamental cycle of a scheme was the fundamental cycle of the schematic inverse image of the scheme. And schematic inverse image of schematic inverse image is schematic inverse image by the composite, and therefore we have finished proving what we want. So that shows that, so identity we already said, this because pullback of schemes, etc. And so, well, I go on explaining this, I don't know why. Okay. So clearly this slide is written underestimating the audience. So take a quick look and I'll shift. You see here there is also involved that if I have two flat morphisms of constant relative dimension, the composite that I already said yesterday is a flat morphism of relative dimensions which add. And so there's a category whose objects are algebraic schemes and whose morphisms are flat morphisms of various constant relative dimensions. On this category, cycles is a graded abelian group functor. And for this functor, the morphisms, which for us are flat morphisms of constant relative dimensions, correspond to graded homomorphisms of a certain non-zero graded degree. And that non-zero graded degree is the relative dimension. So we have functor on cycles, okay, pullback functor on cycles. Now our job starts. We want this to descend to the Chow groups. So we want this to preserve rational equivalence. Okay. So rest of today's lecture and half of tomorrow's lecture will be devoted to proving that this pullback preserves rational equivalence. So we will follow this proof. There is a proof in Fulton, and I thought of writing a simpler proof. This simpler proof is a very straightforward idea, and I am sure all the experts understand such things. But for people like me and you who are outsiders, you may one day become insiders, I must at this point confess that I am an outsider to the whole field of intersection theory, algebraic cycles and whatnot. I was roped in to teach in this workshop because I have some perhaps reputation as a teacher. Okay? So I had to read this stuff myself in order to prepare these lectures, and when I started reading the first chapter of Fulton, I didn't understand it, and I thought it's needlessly complicated how to preserve rational equivalence under pullback. There a straightforward idea should work. So I worked it all out and wrote this, okay, for the benefit of all others like me, while the experts who might understand all this and much more are busy proving cutting-edge theorems. So they are not going to waste their time writing such simple ideas in great detail, which I have. Okay? Because when I thought of this very simple proof, I went to Google search, started searching. Nowhere is it nicely written in all details, nothing. But there is indication that such ideas in some form are not just this, but in far greater complexity, well understood by the experts. So, if nothing else, there was a gap in the literature. Not a gap in knowledge, but a gap in literature is how I will now characterize it. So, I filled it. So, this will be published for the benefit of other readers like me and young readers who are not the aforementioned experts who are busy proving cutting-edge results, but are trying to learn the basics, figure out. So, I am going to give this very straightforward proof. But after writing this straightforward proof, I also realized that the convoluted proof, as I call it, that Fulton gives, has certain ingredients which are generally useful. So I also in my lectures included those ingredients and I have put them to some other use. So the universal property of Chow groups that I keep harping upon comes out of those other tricky properties or other straightforward properties which Fulton uses in a tricky way to prove flat pullback. Those properties I will again straightforward use to prove the universal property. So therefore I have included those properties and shown a use also. Okay. Again, if you look at Fulton doesn't mention the universal property of Chow groups, but if you look at internet sites, experts' stray remarks, they know it very, very well. Have they written it out in this much detail? No, because for them it's obvious. So this you will increasingly encounter as you enter an advanced area of mathematics. There's a whole amount of stuff that the experts know, which is of an elementary kind, and they have not written it up in some simple to follow way for beginners. So this is increasingly so as you advance in a subject, and then at some point you also become an expert and you say, of course, if I have half an hour to waste, I'll write the proof of that, but it's clear to me. And a whole lot of mathematics is in that form. Gradually more and more of it gets written down, but then much more gets discovered meanwhile, which is still in. And so there are vast areas of advanced mathematics in which the proofs are not really written in all detail and pinned down. Okay. So all this was my apology for writing up my proof and publishing it. So let's go on. So my idea is this. If only I could show that a Weyl divisor pulls back to Weyl divisor, then I'll be home. Now, why shouldn't a Weyl divisor pull back to a Weyl divisor? I have variety V and on that I have rational function. I take the schematic inverse image of the variety and I pull back the rational function there. I have rational function here and its Weyl divisor must be that. Objection number one. That pullback of the variety is not a variety. It's a scheme. It has nilpotents. Objection number 2. What do you mean by rational function on such things? If something was irreducible, reduced, an integral scheme, it has its generic point, and that stock is a domain, is a field, and that is the rational function field. Or I take a non-empty open subscheme, that spec of a domain, and the fraction field of that domain is the rational function field. Now here you have some scheme, not irreducible, not reduced. What do you mean by rational function? So I have to answer those things. So these things have answers. So I'll explain those answers. So the long expanded notes that I have written for you, the first chapter of that tells you what is meant by meromorphic functions on a scheme. Now one may think that, oh, go open EGA and read it there. Unfortunately, the material in EGA on this has a fundamental mistake. And this mistake has propagated itself into some other popular textbooks in algebraic geometry. And so I thought I'll rather write everything nicely and make it available. So, do experts know this? Yes, of course. Who discovered that there is this mistake in EGA and all these other people who have copied? Kleiman discovered it. And Kleiman wrote a little 3-page or so note in Enseignement Mathematics around 1970 or very long ago in history, or maybe a bit later, because since Hartshorne repeats the mistake, Kleiman's note must be after Hartshorne. Anyway, so the mistake is well known to experts. Where is an account free of mistake where you are explained what is the analog of rational functions on schemes and how to use it? There isn't any. So as far as I could find. So I had to write one, and that is also part of this. And that's part of, in slightly even more expanded manner, that's part of the notes that I've given you. So read that and learn what are rational function analog meromorphic functions on a scheme. What is required for all that to work is that the scheme has to be locally Noetherian. Only then it works, and the ingredient which makes it work is the basic theory of associated primes on Noetherian rings. Why do I need Noetherian rings? Because on Noetherian rings you have good theory of associated primes, and therefore you can tell what are zero divisors and be able to manipulate zero divisors. Why are zero divisors important? That's because we said that the rational functions on an integral scheme are the fraction field of that ring A, spec A is an open subscheme there. So to take fraction field, I take A upon B where B is not equal to 0. Suppose my ring is not 0. Can I take A upon B where B is not 0? No, I cannot. Problem is, I might innocently take A upon B. I might write this element A upon B. B is not equal to 0. Visible? No. I might... I do it here and there is another end there. I may write, yeah, A upon B, B not equal to 0. Suppose I try doing it for any ring A. But suppose that B times C is 0. Then this, by your rules of localization and whatnot, will be, and C is not equal to 0. Suppose I have such a situation. This will be AC upon BC. And that will, this denominator is 0. So I end up in the situation of having 0 denominator if I simply try to divide by something which is non-zero. So what I want is there shouldn't be some C such that C times B is 0 where C is non-zero. In other words, B should be a non-zero divisor. In other words, B should not lie in any associated prime. Okay? And then, why? Because the ring is Noetherian, there is this translation. Once I have it in terms of prime ideals, etc., I can do my usual manipulations with prime ideals, prime avoidance, all kinds of things I know about primes I can use and handle happily such fractions where the denominator is not a zero divisor. I can define this total quotient ring as it is called by simply saying that A upon B where B is not a zero divisor, but then I have no control on the zero divisors unless the ring is Noetherian. Like what happens under localization, what happens in a stock, what happens under pullback. Okay, how about pullback? What happens under a pullback? In other words, okay, I must talk algebra. If A to B is a ring homomorphism, and I take a fraction x upon y, where y is not a zero divisor, and I take fx upon fy, but fy might be a zero divisor. How do I prevent fy not being a zero divisor? If f is flat. Because zero divisor means, so I have this x upon y, and multiplication by y on a to a is injective because y is not a zero divisor. So now when I base change to b, which means tensor with b, I get multiplication by y from b to b. Because this is injective and because this is flat over this is injective. So I can handle these total quotient rings in a Noetherian situation provided the ring homomorphisms are also flat. And that is really the situation I am working in, and this has disappeared. Okay. Okay, so I want to show that pullback of rationally equivalent to zero cycles is rationally equivalent to zero. Rational equivalent to zero cycles come as Weyl divisors of rational functions. I can pull back those functions to get meromorphic functions upstairs, because algebraically the whole theory is based on non-zero divisors going to non-zero divisors under flat morphisms. This does not require relative dimension to be constant, this part. So the good behavior of meromorphic functions and non-zero divisors with respect to ring homomorphisms is for flat. There is no notion of dimension involved there. But because we are applying it to cycles also, we want that to be both flat and of relative dimension, some constant. So once that happens, so I already explained my working philosophy to you. We are going to use the general concept of the ring. This A upon B, such things are not going to be a field. Okay, they are going to be a ring. So for the ring of meromorphic functions, we are going to work with it. And in this ring are the invertible meromorphic functions. Earlier I had non-zero rational functions for which I took Weyl divisor. Now I shouldn't talk of non-zero. I should talk of invertible. So just a little aside, since all graduate students know this, is typical entrance PhD exam question. So what is GLN K, where K is a field? Yeah, n by n matrices over the field K such that determinant is non-zero. What is GLN Z? What is GLN A, where A is a ring? Determinant has to be a unit. What is important about determinant being a unit? Because in the formula for inverse of a matrix, you have the matrix of cofactors divided by determinant of the matrix. Right? So you want to be able to divide by the determinant of a matrix. And over a field, you can divide by anything non-zero, which is why you say, oh, determinant non-zero. So same kind of thing here. A rational function non-zero really means rational function is invertible. What I want are invertible functions. So I take invertible meromorphic functions, and then I can talk of their Weyl divisor. So we have this general theory of meromorphic functions as given in EGA. Where in EGA? EGA 4.4. EGA 4 has 4 volumes. At breakfast we were discussing this in some funny context. EGA 1 has 1 volume. EGA 2 and 3 together have 3 volumes. And EGA 4 has 4, well, I shouldn't call it whatever, 4 connected components. You can physically. Okay. So this is the 4th part of 4, and precise reference, I think section 20 or something, is where the basic theory of meromorphic functions is given. And it has all kinds of correct things, but for this basic mistake he is making of not assuming locally Noetherian, because of which the non-zero divisors are very badly behaved. Rest of it is correct. But anyway, I didn't read it. So I increasingly find it, or over decades I increasingly found it far easier not to read but to just get the idea by glancing and then sit down and fix your proof. See, finally, all mathematicians have to have certain amount of technical ability, the ability to lift something. Okay? Except you don't know what to lift and where to carry it. And that comes from the great mathematicians. They tell you, oh, this can be done, then this will happen, then this will happen. But if you try to read how they do it step by step, I find it very difficult. So it's much easier to say that, you have to go from here to here to here, and then there's a rock which you have to climb, and then you will go to the top. Roughly that is the route. Okay, now I'll climb. And the little skill that how to put your leg, how not to slip, how to catch somewhere, are the skills of mathematicians, right? There's no genius required there. Just some hard work and patience, and you little cleverness perhaps. Instead of going like this, you go like this locally. But the great strategy is work of genius. Rest of it is technique. That's why you guys have to go on doing exercises, till you develop that muscle which allows you to do all this yourself. And you say, okay, I know how to make that work. Give me half an hour. If needed, I can write down the proof, but I'm not going to waste it right now. Let's get on. You should be able to say that with confidence and do it when challenged. And that's why I say, challenge yourself time to time. Go back to the very basics on one of the steps. Do it on some sample step. You don't have to do it for every step. Okay, let's do that. Let's apply it to this. I have this flat morphisms of F inverse V to V. This is a variety, this is a scheme. And that's going to give me a map of the total quotient rings from here to here because of flatness. And under any ring homomorphism, an invertible element goes to invertible element. Because x into y equal to 1, therefore fx into fy equal to 1, therefore fx is again invertible. So the invertible meromorphic function gets pulled back to invertible meromorphic function. And there I take its divisor by that same formula, multiplicity of vanishing of an artin local ring. So where does non-zero divisor come in? There. Because I go modulo by a non-zero divisor, if I take a Noetherian local ring of dimension 1 and go modulo by a non-zero divisor, then I get an artin ring. Because this non-zero divisor, what are the zero divisors? The union of associated primes. Are minimal primes associated? Yes. So that means this is not in any minimal prime. So when I go modulo this or take the closed subscheme defined by some small x equal to 0, that's not going to contain a component. The components look like this. And I am going to cut it. And this is a equal to 0. And it cuts every component. Because this a is not in any pi. Because it's a non-zero divisor. Okay. So then each of these cuts becomes dimension 0. I get an artin local ring because I have non-zero divisor. So it has a length. And so I can weigh everything by its length by the same formula and define the fundamental cycle of this invertible meromorphic function. Define the Weyl divisor of this invertible meromorphic function. So I am telling you that if I have an equidimensional scheme and an invertible meromorphic function on it, the same formula for a Weyl divisor of a rational function gives me Weyl divisor of this invertible meromorphic function. Crucial step, why do I have artin rings so that I can write length? Answer, because I have non-zero divisors. Okay, so that is how I produce pullback of the, Weyl divisor of the pullback. And now I want to check that if I pull back the invertible meromorphic function and take its Weyl divisor by this method, or I take the Weyl divisor of that rational function on that variety, which is a cycle after all, and I know how to pull back cycles. Take each of the constituent varieties, pull it back, that's a scheme, take its fundamental cycle and add them up by the same whatever given coefficients are. These two are equal. If I show that, I am through. Okay. Now this equality I can check sheaf theoretically. Okay. So as I struggled my way through Fulton chapter 1, I couldn't see the word sheaf. And what I immediately saw after his definition of cycles, hey, this is a sheaf, this is something local. So I thought I have made a great discovery that this is a sheaf, but on searching literature I found a paper of Rost later, and Rost is well aware that all these things are sheaves. And what is he doing with that? Something very advanced, which I don't understand. So same problem. Experts know all this and they go up. Okay, so cycles form a sheaf, which I said some time back. The boundaries don't form a sheaf. It is the same problem with de Rham cohomology. The closed differential forms sheaf condition. You can check locally. I have closed forms which match locally, overall the form is closed, or that they are closed can be checked locally. Its exact cannot be checked locally. Exact is not a sheaf condition. So the cycles form a sheaf. The rational equivalent to 0 don't form a sheaf. But so when I want to check equality of sheaves, I can check locally. I can go affine locally, do algebra and check it there. So that's what I do. And so this property, I want to check this equality on a scheme. That scheme I will cover by affine open subschemes and check the formula locally. But you may say there are two schemes involved, X and Y. I am pulling back. So what I will do is I will take an affine open cover of Y, and for the inverse image of each of that affine open sets, which is not affine, I take smaller affine open sets which cover that, each of which is now an affine open subscheme which is mapping into an affine open subscheme. And for this I can do algebra. And so for the affine open cover upstairs, so defined, I check the equality. And I have the equality. Yeah, strategy clear? I am giving you a hand weighing proof because I have written the proof in detail twice, once in my archive preprint, which is available to you, and even in greater length in my accompanying notes, which have been emailed to you. Okay, so I am allowed a hand weighing proof to focus on the main ideas. Because I believe you are like me, instead of reading line by line the proofs I have written, you will also like to understand the ideas, and then you will like to use your own technical power to fix the details. And please try that, and if you get stuck, go consult that. Okay, so this is the local checking one has to do. So an exposition of the basic concepts of meromorphic functions is given in section 1 of the detailed notes. This N is the detailed notes I have given you. So it begins by saying what's the total quotient ring of a ring. That's a localization of A by inverting the subset of all non-zero divisors. And this, because any scheme is locally affine, allows me to define a sheaf. The Noetherian condition is what is needed to say that all this is well behaved. Okay. I might have an open subset on that a non-zero divisor, and I might have a smaller open subset. How do I know it restricts to a non-zero divisor? And all such problems come up, which can be solved by appeal to Noetherianness. What about the stock? Is the stock obtained by taking the stock of the structure sheaf and localizing it with respect to non-zero divisors in that stock? Will this be the same as the stock of the overall sheaf of meromorphic functions? So all such equalities are indeed true and depend on Noetherianness at every step, because they depend on a good understanding of how non-zero divisors behave under localization, and you know how prime ideals behave under localization. What are the prime ideals in the localization S inverse A? They are prime ideals in A which do not meet S. So you see, because you understand the behavior of prime ideals with respect to all such basic operations, you are able to convert that knowledge into how non-zero divisors behave, provided non-zero divisors are linked with prime ideals, which happens when the ring is Noetherian. Philosophy is clear? Okay. So various nice things happen, let's say, as you would expect by common sense, which Grothendieck expected by common sense, and that's why he made those mistakes in EGA. What he writes there is correct, What is missing is a Noetherian condition. Why is Noetherian condition missing? Because Grothendieck does not want Noetherianness. And a whole lot of EGA4 is devoted to techniques which allow you to circumvent Noetherianness. Why should you want to circumvent Noetherianness? Because you may begin with nice schemes which you want to understand, which are Noetherian. After all, classical algebraic geometry only dealt with finite type K algebras. But number theorists are also now on board, therefore there are these other rings, but they are also Noetherian. Now, but what happens is we need analytic techniques, we need completions. Once you pass to completions, they are no more essentially finite type over your K. Now you do operations with these, you take the tensor product, you are out of Noetherian state. So you may begin with Noetherian things and do the kind of operations that are needed, especially things like completion, and then you get thrown out of completion itself may be Noetherian, but two such completions over the base, their tensor product, no chance. So you get pushed out of Noetherianness very fast. You want to be able to prove all your theorems even when the rings are not Noetherian. And so EGA is reluctant to make the Noetherian condition as much as possible to show techniques how to do it. I think I want to bring to the attention of the young students the name Brian Conrad. Maybe many of you have already read his things. Read his lecture notes and whatnot in general. He has done a great public service by putting a lot of his writings in the public domain, and he takes the pains to explain difficult things to people like me. And what experts very rapidly write, he tries to write in all detail. For example, he tried to write a proof of Grothendieck duality. Okay? Take the proof in literature and really write in all details, and then he got into trouble with science and all kinds of things happened. Okay? On the other hand, there are out and out geniuses who will approach Grothendieck duality by a completely different way and just give a fantastic new approach to it, like Niemann, Amnon Niemann. But I don't know whether somebody like Conrad reads the proof of Niemann. He might produce another longer exposition which rest of us can understand. So please look at the writings of Conrad. I was suddenly reminded of this because Brian Conrad tries to explain a bit of how to circumvent Noetherianness and techniques for it in EGA and whatnot. Anyway, so I have told you why EGA went wrong on this point, because Grothendieck's reluctance to assume Noetherian. Read those parts of EGA and in your mind all the time add Noetherian, and then it's all correct and you have a lot to learn there. Okay. So a non-zero divisor maps to non-zero divisor, blah blah, I already told you. So there is this F upper sharp which goes from otherwise F inverse OY to OX, gets converted into F inverse KY to KX. And it maps this into this, invertible into invertible. And with this pullback, I have this obvious property that pullback of a meromorphic function is the pullback of the meromorphic function by the composite. So I have this property for cycles themselves, I have this property for the meromorphic functions themselves, and therefore by comparing this, I want to know that if I have a meromorphic function and I convert it into a Weyl divisor by my expanded definition of Weyl divisor, or I pull it back flat and convert it into Weyl divisor, that's the pullback of the earlier Weyl divisor. And for this second pullback, I'll assume it is flat of constant relative dimension. Just to pull back the meromorphic function, I don't need constant relative dimension. Okay? So I want a commutative diagram. So in all these slides there were no commutative diagrams, right, so far. That's because it's too painful writing them on slides and making them fit. But all the time in my mind I have been carrying commutative diagrams, this commutes, this, therefore is this, blah, blah, but writing it in straight lines here. Okay, in your mind it should be back to a two-dimensional picture. So at this point I am saying something like, I have x to y, flat, relative dimension, constant relative dimension, and so I have This is F, so this is F sharp. On the other hand, and these are of equidimensional, of dimension something. This is also equidimensional, because I am going to apply to that closed subvariety Y and its inverse image and whatnot. For my pullback, I am not assuming the schemes are equidimensional. I am going to apply to closed subvariety. Just as earlier in the proper business side, my morphism was not surjective, but the argument came via surjective. So I have this. From here, this is suppose dimension n, and this is dimension n, and this is n minus m flat of relative dimension n minus n. So from here you will go to z n minus 1 of x. This is taking the Weyl divisor on x. This is taking the Weyl divisor on y. And this is the pullback we have defined at the level of cycles. This commutes. This is the main technical thing to show. Okay. So I have a Weyl divisor, which is the Weyl divisor of certain rational function. Its pullback is also the Weyl divisor of a rational function. Which one? The pullback of the rational function. Or I have to call them meromorphic functions now instead of rational. Okay. So this commutes is the main point, and then the proof is through. Understood? Oh, misprint. Thank you. And that shows you are awake and paying attention. Okay. So this commutes is the main point. And that therefore involves doing algebra. Because for this to commute, this cycle, everything is based on closed subvarieties of dimension n minus 1. I have to go to their stocks there and check whether the multiplicity is right. So everything gets reduced finally to some commutative algebra being done with Noetherian local rings and flat extensions and what happens to multiplicities. And that is done in great detail in my notes. Okay? Or in even more detail in my archive version. So go read it there. Writing algebra line after line is something which I don't think is a good idea in a lecture, because algebra is something which you have to do with your own hand, not the spectator's sport. But the ideas can be explained and you can read the proof there. So I explained the ideas, how it finally comes to some algebra done with one-dimensional local rings and the resulting Artin local rings after going modulo non-zero devices. So we have already defined the order function on one-dimensional Noetherian local domain. By this generalizes to an order function. This is a non-zero divisor. A non-zero divisor has an order, because when I go modulo non-zero divisor, I get an Artin ring. Otherwise, I don't. So the order function extends to this. Same definition, because this is now Artin. And as it converts multiplication into addition, it extends to a total quotient ring. So therefore, the meromorphic functions also have an order, and so one can define the divisor and define the Weyl divisor by the same formula, because now we have the concept of order. This I had orally said, but now you see it on the slide. Okay, I'll leave this slide on for 15 more seconds and then turn the page. No, there is no page to turn. I have reached the end of it. 4.10 and 8 minutes to spare. So I have been finishing my lectures about 7 minutes, 8 minutes ahead of schedule. That's great. Nice. So I'm going to stop there and, well, give you a glimpse of what follows. So we have to prove it. I have to do that local algebra. I am going to show it to you. I am going to show it how to carry out to the bitter end. In all cases, I am going to show you how to do it. Just as there we did the case relative dimension, blah, 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 blah. Here it's going to be affine, glue it, whatnot. And that is the comment I already made. This completes our treatment of flat pullbacks. This is all going to happen tomorrow. And the proof in Fulton is tricky but has some independently useful ingredients which are proper push forward, which we have already proved but which we don't use here. A certain important proposition called push forward and flat pullback commute with each other. Flat pullback of relative dimension constant. It's called push pull equal to pull push. That is part of Fulton's proof. I don't need it because my proof is very straightforward. It is tricky. And the third thing, the trickiest of all, is how to represent rational functions in terms of morphisms to P1. Okay, this is a nice trick which he employs. I don't need it. And so, but I explained this trick. And that is the trick we will use in proving the universal property of Chow groups. Okay, so I will do all the ingredients of Fulton's proof which are otherwise useful. And you can ask, how does Fulton put together this and complete his proof? That now you can read in his own words in his book. Okay, or I can tell you, you ask me outside. So this is what is coming. Let's go back to. So this page you understood. So let's go back to the list of slides. So what we did today was we defined the fundamental cycle of an equidimensional scheme. That's where that picture came up, that it has certain thickness, different thicknesses. So we take the top dimensional components which are of the same dimension, irreducible components, and take the length, amount of thickness, counted at generic point, therefore it's length of the Artin local ring, just the generic stock at that point, and define the cycle. Then we define flat pullback on these cycles. Then we define flat pullback of fundamental cycle, and pullback of pullback is pullback. That is the functoriality of flat pullbacks. And then came flat pullback preserves rational equivalence. This was the main point. And for that we had to introduce the idea of meromorphic functions, because the pullback was not a Weyl divisor of a rational function, because there are no rational functions on the schematic inverse image of a variety, which is not a variety, may not be a variety. Then how do you handle it? So you have to expand the notion of rational functions to all these other schemes. Those were meromorphic functions on Noetherian schemes. And then to such you associate Weyl divisor by the same formula. Formula works because you are going modulo non-zero divisor, therefore it's still an Artin local ring. Okay, this is the whole story of today's lecture. Going modulo non-zero divisors means when you cut by that, that cut doesn't contain some entire irreducible component. Every component is getting cut. Why? Because that thing, for it to contain a component, which means that thing has to belong to one of those primes. Those are minimal primes. That would make it a zero divisor. Why is an element of a minimal prime a zero divisor? So I am asking you today, well, I don't know whether today's... Well, I am asking very simple. P content A is minimal. Then any A belonging to P is zero divisor. Localize, then what? This is an Artin local ring. And this A lies in PAP. In an Artin local ring, the maximal ideal is nilpotent. Why? Well, you may say the nil radical is the intersection of all prime ideals, and here there is only one prime ideal, and so all of them must be nilpotent. So some power of A is zero in this localization, which means it is killed by something not in P. So A to the power n times P equal to 0, where B is not in P. Now if A to the power n minus 1 is already a zero divisor, you are done. Otherwise all this, so now by induction on n, A times A to the power n minus 1 times B is 0. So, and so on, so on, so on. So by induction on n, this shows that A is a zero divisor. Okay? So anything in a minimal prime is a zero divisor. So because we had something which is a non-zero divisor. It was not contained in any of those minimal primes. Therefore, when you cut by that, go modulo, that doesn't contain any minimal prime, and those were dimension 1. What is left is dimension 0. So it's an Artin local ring, therefore it has a length. And that is why the fundamental cycle is definable, because the thickness is this length of this Artin local ring.